Welcome to qnawire.
In this problem, we're going to be looking at this sphere of helium gas here. And given the geometry of that sphere, the pressure of the gas inside and its temperature, we are going to determine the number of helium molecules in that sphere. So the first thing we'll probably want to do here is determine what the volume of this sphere is. And we can recall from our geometry knowledge that the volume of a sphere is 4/3 pi r cubed. In our case, r, the radius of the sphere, is going to be half of the diameter, which is 15 centimeters, or 0.15 meters. Okay, so now to actually determine what the number of molecules of helium is inside this sphere here, we will refer to one of our equations for an ideal gas that we derived from the molecular model of gas, which was that the pressure is 2/3 times N over V times the average kinetic energy. And of course, the average kinetic energy of a molecule in an ideal gas is 3/2 kBt. So if we substitute in our value for K here, well, actually, first let's solve for N. So if we solve for N, we'll have 3PV over 2K is equal to N. Then we can substitute in our expression for K up here. So we'll have N equals 3P, and we'll leave V out too because I'm going to substitute that in as well. So divided by, or a 1 over K is going to be 2/3 times 1 over kBt. So we get to cancel these out. And then V is going to be 4/3 pi r cubed. So if we simplify that now, we will have that N is equal to P over kBt times 4/3 pi r cubed. Awesome. So now all we have to do is make sure that we have the right units for everything. We've already converted R to meters. We should convert our pressure to pascals. So I believe we had 1 atmosphere worth of pressure, which is just equal to about 1.01 times 10 to the 5th pascals. And then our temperature is in degrees Celsius. So we will want to convert that to Kelvin. So that's going to be equal to 293.15 degrees Kelvin. Okay. So everything's converted. All we have to do is plug in these values now. And if we do that, the net result here for big N is going to be 3.54 times 10 to the 23rd molecules, which is about half a mole. All right. Now, given that we know this, let's try to determine what the average kinetic energy is of a molecule in this helium sample here. So one thing we could do is we could refer back to this equation and just solve for K now instead of instead of N. Or we could just use this 3/2 kBt here, and they should come out to the same thing. Using 3/2 kBt is probably slightly a slightly more simple calculation, so we'll just do that. So K equals 3/2 kBt, where the Boltzmann constant is 1.381 times 10 to the minus 23rd. And if we calculate that, we will get 6.021, actually 6.07, read that off wrong, times 10 to the minus 21st joules. All right. Now, one last calculation. Let's look at what the RMS speed of a molecule in this gas is. So VRMS, root mean squared velocity, is just equal to the square root of either 3 kBt over the mass of an individual molecule, or 3 kBt or 3 RT over the molar mass. Which I tend to prefer this one here because the molar mass is generally easier to remember. So for helium, the molar mass is just 4 grams per mole. Or of course, if we convert that to kilograms, we will have 0.004 kilograms per mole. And then everything else is in its proper units. So if we plug and chug all those numbers in there, we should get that the root mean squared velocity is about 1,352 meters per second. So there you have it. We determined what number of molecules were in this helium sample given its geometry, pressure, and temperature. And then we did some more calculations after that, specifically the average kinetic energy of a molecule in that gas and the root mean square velocity of a molecule in that gas.